assume you asked.
All right, any questions?
Is test 1A still on Wednesday?
Yep.
Okay.
Chapters 2, 3, and 4. It is written, it is too long. But I'm not taking it, so no, I need to pare it down some.
Do you have any study suggestions? Like,
Look at the old tests.
okay.
All right. We last left off. What was the example that we last did?
I think it was the block sliding.
Okay, we finished that?
Yeah.
All right. Next one. All right, so that's the problem we're going to work with right now. Just going through the exact same process as we've been doing. So, what's the first step? Okay, just don't tell Michael. All right, so what's the first step?
Choosing one of the things. Law of gravity. Right?
Okay, you said law of gravity?
Or, what was it? Force of gravity?
Okay, force diagram?
Force diagram.
Okay, do force diagram. Now, for a problem like this, we have this wedge that's attached to the ground. I did not draw it as a separate object. So what we really care about are just these two objects. If you want to do the full force diagram, that's fine, but I really only care about these two. That's my 3. That's my 5. So you can make a chance to do all of them. What are the forces acting on these masses?
Gravity would be one.
What's the force? Yeah, gravity is a huge topic.
Right.
Weight.
I forgot what it was called. Oh, wait. Yeah.
Yep, that works. Weight acting which way on the objects?
Towards the center of the earth.
Sure. So I got W, I'm gonna label it W's of 3 and W's of 5. All right. And then there's 2 arrows pointing up on the earth, but I don't have to draw those. So gravitational force done.
The normal force
Acting on what, which way?
on the 5 kilogram block perpendicular to the surface of the wedge.
So that way or that way?
That way.
All right. So we got normal force going this way. Acting which way?
Up on the 3 kilogram box and, parallel with the ramp on the 5 kilogram.
Alright, so normal was done, tension's done, what about friction?
Frictionless.
Did you say it then?
It's frictionless.
Yeah. So, and other?
No,
Said no?
yeah,
Why not?
because you don't specify any other forces.
Yeah. The Maradona hand of God.
So if you were to say other, then would you like draw something that was pushing upon the
Yeah,
box?
all right, I put it in the text that something else was involved.
Gotcha.
All right, so we have, so we have our force diagram on the force of the two forces that we really care about. What's next?
We could calculate the weight of each block.
Oh, we could, okay. Let's make life simple. Let's put this on a strange planet where G is 10 meters per second squared. I don't think there's any place on Earth that actually makes it that far, that high. So what's the weight of the 3 kilogram mass?
30 newtons. And 50 newtons.
Okay. That, I typically would have waited on that, but it is not wrong. What is the next step in the process?
We can set up an equation to find the normal force.
Not there yet. Or we could work backwards from that. If we work through a problem, but written up the mnemonic. Force diagram, what's next?
Acceleration.
Yeah, what about it?
Finding the acceleration of the 5 kilogram blocks.
Not actually finding the acceleration, that happens down here. What's this next step after we have our force diagram? Before we come up with our equations. Before we decompose any vectors. Before we come up with our coordinate axes.
Oh, we determine if there's any change in acceleration.
Not changing acceleration.
Just which way it might be.
Yeah, we have to get the direction of acceleration. Now, what is the direction of the acceleration in this problem?
Towards the ground.
Equilibrium should be accelerating, right?
All right. Now, if it did move, let's reword that. It is an equilibrium, there is no acceleration. However, we do have to figure out a direction because we need to come up with our coordinate axes. So,
Well, either 3 kilogram goes down or the 5 kilogram goes the other way. Depending on the angle.
right. So were you making the suggestion to just pick this way? Or are you
Not
just,
necessarily, I was just saying.
okay. Well, I've drawn it up now.
Okay.
You pick one way or the other, it doesn't matter, just so long as you're consistent that the magnitude of this mythical acceleration would be the same for both. So now once we decide a direction there, we set up a coordinate system. The coordinate axes. So if I'm picking down to be positive here, then well, make that positive. If you want to put a letter into it, I'll make it I3 hat. If you don't like I and would rather use J, that's fine too. All right, so for the 5 kilogram mass, if this is positive direction there, then positive has to be up the ramp also, unless we want to mess with something later on. So I'm going to call this the I5 hat, and then perpendicular to it is the J hat. Which way do you want to make J hat? Away from the ramp or towards the ramp?
Away from the ramp?
Okay. You put a question mark in there. You went up at the end of your sentence.
Oh,
Right.
away from the ramp.
Okay. Is he right? Or perhaps the question, is he wrong? Are you,
He's right.
he's right? Okay.
Yeah.
If he'd gone the other way, would he have been right? Yeah. It doesn't matter which way you go, so. He is not wrong. All right, now we've established our coordinate axes. Do we need to break anything up? Are there any vectors that are not parallel, anti-parallel, or perpendicular to the coordinate axes for that mass?
Yes.
Which one?
The gravitational pull.
Okay, we're gonna need to break weight up. I have this angle of theta there. So I got normal force stays the same. I have this tension stays as is, and I'm breaking weight up into its components. We've gone through this before, but this would be W5 sine of theta. W5 times the cosine of theta. Questions to hear before we do our equations?
Will there ever be a problem where we don't have to find which way the box accelerates?
Well, in this case, it's not going to accelerate because it's in equilibrium.
Right.
So this would be as close as you get to that.
Okay.
All right, our equations. How many equations of motion will we have?
Three.
Like you mean it.
3.
Yes. We got one here, it's got one dimension here, we got 2 dimensions here. So 1 plus 2, which the math people tell me is 3. And again, if the math people are aligned, then civilization will collapse. All right, so we'll have I3 hat, I5 hat, J5 hat. Those are our 3 equations. Someone take a chance. Give me an equation.
I3 hat equal to would be equal to I5 hat if they're at equilibrium.
These are just directions, so
Oh.
the directions are not the same.
Oh, okay.
Would it be the tension minus the weight, or no, it'd be the weight minus the tension,
Why is it weight minus tension?
since down is positive.
Okay, so we got W3 minus the tension equals,
Mass times acceleration.
well, which mass?
3 kilograms.
And what's the acceleration?
0?
Yep. I've had students, I've given students in the past equilibrium problems on tests, and they get to the point where they're going, I don't know what the acceleration is, and there's not enough information. That it's equilibrium, acceleration is 0. All right, next, 2 more equations to go. This doesn't necessarily have to be the moment, but Osama, I haven't heard your voice yet.
So I was trying to find the one that we did from last time.
Okay. I've now heard your voice.
Hmm?
I've now heard your voice.
Oh, yeah.
Then you have to look like you just want to show off right now.
I don't know about that. Weight 5 sine theta. For I had 5.
Okay?
Yeah.
So W5 sine theta.
Minus tension.
All right, you have minus tension.
Yes.
How are we gonna finish that? All right, so you have that minus tension equals,
Mass 5 times acceleration.
we can narrow it down better than that.
0.
Yeah, all right. Now, in this particular case, what you have written, what is written here is fine. As far as the process is concerned, we had the positive direction that way.
Oh,
So tension minus the weight.
yeah. Got it.
Tension. And one more to go.
W5 is equal to
You're looking at this.
yes.
So W5 is equal to,
W cos theta plus W sine theta, W5.
as long as you put vector symbols over it, then that is a true statement. Sort of going
It's not
backwards. though.
helpful.
No.
Would it be the normal force minus W5 cosine theta? Equals M5, 0.
Yeah, they'll, when we set it, as soon as we set up the coordinate system, strongly recommend you stick with that. So that way it's positive, so we have normal force minus W cosine 5 cosine theta is equal to mass times acceleration. All right, we're trying to find the angle. Well, we've got enough information here. We can go for the typical stunning visual effects. I know what W3 is. So we end up with W3 is equal to the tension, which is 30 newtons. Or weight 3 is 30 newtons, therefore the tension is 30 newtons. And then in this equation here, we have the tension is equal to M5G sine theta. So we have 30 is equal to 50 sine theta. Sine theta is equal to 0.6. Theta equals 36.81 degrees. So it's what you reveal. Here it actually is.
Mr. Fox, can you go back over how you got the 0.6?
Are you good with this equation?
Yes.
I'm solving for theta, so I have to first get rid of the 50, divide both sides by 50.
Oh, okay.
Yeah, it's 36.867.
867.
869, sorry.
You get something different, Patrick?
No, I'm just trying to.
Questions before I change the problem? All right, let's change the problem. Theta is doubled. Find A. We still have the same masses. Only thing that we've done is get rid of the equilibrium and change the angle. Now, what is this? By changing the angle, by doubling this theta, which way will this